Welcome to the deep dive. Today, we're pulling back the curtain a bit on something most people don't think about, but it's crucial. We're talking about the hidden highways inside our computers, our devices. Things like PCIe, Peripheral Component Interconnect Express. Now, these aren't just tech jargon. They're like the fundamental I/O backbone, quietly powering everything. Basic web browsing right up to, heavy-duty AI stuff. And for 2 decades, PCIe's story was mostly about speed, getting faster and faster.
Right.
But the world it lives in, that's changed dramatically.
Yeah. We've gone from, let's say, physically locked down data centers to these enormous cloud environments where lots of different people share the same hardware. And in that world, you can't just dismiss the idea that maybe, just maybe, someone malicious could get physical access to a server. And that opens up a whole different can of worms. Hardware attacks, stuff that software security just doesn't see. We're talking like plugging in bad peripherals or cards that literally sit between components to spy on data.
Alter it. Right, alter it. Or even PCIe switches that have been compromised.
Yeah.
Or replay attacks capturing real data and just sending it again later.
It's sophisticated stuff. Imagine someone with lab gear poking around inside or firmware designed to just pump out malicious packets.
And this bypasses all the usual software protections. Could lead to massive data theft, system manipulation.
Yeah.
It's serious.
Absolutely.
So, where does PCIe 6.0 fit into this? Because it sounds like it's not just about speed anymore. It's like a whole new game for security.
Right.
But how did that happen? How did this standard that was all about raw speed suddenly become this security powerhouse?
Well, that's the really interesting part. Security in PCI 6.0 isn't just bolted on. It's not an option you tick. It's actually deeply fundamentally linked to the technology changes that make Gen 6 what it is, older PCIe versions. They had some basic protections, sure, but mostly relied on the system, like IOMENUs, to fence things off. PCI 6.0, though, built a whole security framework right into the spec from the ground up, really designed to tackle these modern physical threats head on.
It's funny how sometimes the biggest changes come from, unexpected places. Not the direct goal, but a consequence. So if the main push for PCIe 6.0 was speed, how did chasing that bandwidth accidentally force all these security upgrades?
That's exactly the question. That's where the whole story kind of unfolds. The core driver, doubling the data rate. From 32 gigatransfers per second in Gen 5 to a massive 64 GTs in Gen 6. But the old trick, just cranking up the frequency, that hit a wall.
Why? Just too much noise.
Pretty much. Pushing frequencies that high on regular circuit boards, the signal just degrades too much. Channel loss becomes a nightmare. Think of it like shouting across a really noisy room. The higher you pitch your voice, the harder it is for anyone to understand you clearly. Same idea with electrical signals.
Okay, so they couldn't just double the frequency. What was the clever workaround then?
The big shift was adopting PAM4 signaling, pulse amplitude modulation with 4 levels. It's a totally different way of encoding data, instead of 2 voltage levels for 1 bit like before. Right. PAM4 uses 4 distinct voltage levels to encode 2 bits per signal transition.
Ah, clever. So you double the data.
Without doubling the signaling frequency, exactly. The underlying frequency stays at 16 gigahertz, same as PCIe 5.0. And because it's running at half the frequency of what a traditional NRZ scheme would need for 64 GTs, the signal loss problem is much more manageable. You can still send data a decent distance on the board.
Okay. Sounds great. But there's always a catch, right?
There's always a catch. With PAM4, those 4 voltage levels, they're packed much closer together.
Less room for error then.
Way less room. The signal clarity takes a hit. Engineers talk about the eye diagram closing up. Basically, it gets blurry, harder to tell the levels apart. So your signal-to-noise ratio drops significantly. You get maybe 1/3 the noise immunity of Gen 5.
Oof.
Yeah. And the direct result is way more errors, a much higher raw bit error rate, the BER. More errors than you can really tolerate for a reliable connection.
So that's the paradox. You get the speed, but the physical connection itself is inherently noisier, less reliable.
Precisely. So how do you fix that? How do you guarantee reliability when your foundation is shakier?
Okay, I'm guessing this is where the error correction comes in.
You got it. The mandated solution. Forward error correction, or FEC. It wasn't optional. It was an absolute necessity to make PAM4 work reliably enough for PCIe. But PCIe needs low latency, right? You can't just slap on the heavy-duty FEC you might see in, say, long-haul networking.
Right, that would slow things down too much.
Exactly. So they developed a lightweight FEC. Very low latency. The target was under 2 nanoseconds. Super fast. Doesn't catch every single error, but it catches most of them. And it works hand in hand with a strong error detection code, the CRC. the cyclic redundancy check.
Okay, so FEC fixes most mistakes, CRC spots any leftovers.
And if the CRC finds an error the FEC missed, it triggers a very quick retry at the link level. That mechanism was already there. So this combo, lightweight FEC, strong CRC, fast retry, keeps the link reliable without killing the latency.
Okay, that makes sense. But mandating FEC, I imagine that wasn't just a simple patch. Did that have bigger consequences for how PCI works?
Oh, huge consequences. Massive. It triggered a cascade effect, fundamentally changing the architecture. See, FEC algorithms, they need to work on fixed-size chunks of data, predictable blocks.
Okay.
But legacy PCIe, it worked with variable-sized packets, transaction layer packets, TLPs. They could be short, long, whatever.
Ah, I see the clash. Fixed blocks for FEC, variable packets from the layer above.
Total incompatibility.
Yeah.
And that incompatibility forced the single biggest architectural change in PCIe history.
Which was?
The move to FLATE mode, flow control unit mode.
But a FLAT mode.
In FLATE mode, the basic unit moving across the link isn't a variable TLP anymore. It's a fixed size, 256-byte FLAT. Big TLPs get chopped up and sent across multiple FLAT.
Yeah.
Small TLPs might get bundled together into one FLAT.
So everything going over the wire is now in these neat 256-byte packages.
Exactly. And this was initially driven by FEC, but it brought other nice benefits too, like better bandwidth efficiency, got rid of some old encoding overhead, almost perfect 1 bit in gets 1 bit out efficiency. But here's the kicker for our security story. This rigid, fixed block structure. It turned out to be the perfect foundation for strong, hardware-based security.
How so?
Trying to encrypt or authenticate variable-sized packets is messy, complex, but these predictable 256-byte FLIT-day, they're ideal containers for block-based cryptography like AES.
Ah, okay. So the move to FLIT-TITs, forced by the need for speed in FEC, unintentionally made implementing strong crypto much, much easier.
Exactly. It wasn't just enabled, it was like architecturally invited. FLIT mode paved the way.
That's quite a chain reaction. Speed leads to PAM4, leads to noise, leads to FEC, leads to FLITs, which then creates the perfect setup for security.
Wow. It's a fascinating example of technological evolution.
Okay, so we've got the physical layer sorted and this FLIT mode structure in place. But before you start encrypting data, you need to know who you're talking to, right? Establish some trust. How does PCIe 6.0 make sure that the device you just plugged in is actually what it says it is and hasn't been tampered with?
Right, that's the next critical piece. And that's handled by component measurement and authentication, or CMA. CMA is basically a standardized protocol built into PCIe 6.0. It lets the host system challenge a PCIe device cryptographically.
Challenge it how?
To prove its identity. And also, to get measurements, think of them like digital fingerprints of its firmware and critical configuration. This whole process establishes what's called a hardware root of trust for that I/O device, basically proving it's genuine and hasn't been messed with before you start sending sensitive data to it.
Makes sense, especially in those shared cloud environments.
Yeah, absolute critical there. And the good news is the PCI SIG, the group that defines PCIe, they didn't reinvent the wheel here. They leveraged an existing, well-regarded industry standard. SPDM, the security protocol and data model. It comes from the DMTF, the Distributed Management Task Force.
Okay, using an existing standard is good for interoperability.
Definitely. It helps PCIe security fit into the bigger picture of platform security.
So SPDM is the protocol. How do these SPDM messages physically get sent back and forth over the PCIe link? Is there a special channel?
There is. It uses a mechanism called DOE, Data Object Exchange. DOE is defined as part of the PCIe spec. It essentially creates a standardized little mailbox in the device's configuration space.
Like an inbox and outbox.
Pretty much. The host writes SPDM request messages to the device's DOE inbox. The device processes them and puts the response in its outbox and signals the host. Simple, standardized way to shuttle these security messages.
Got it. So walk me through that CMA process using SPDM and DOE. How does it actually establish trust?
Okay, it's a sequence. It starts with discovery and capability negotiation. The host and device basically say, hi, figure out what versions of SPDM they both support, agree on which crypto algorithms to use, that sort of thing.
Handshake first.
Right. Then comes certificate-based authentication. The host asks for the device's identity certificate, or maybe just hashes of it. It checks this certificate chain against a trusted root certificate authority, usually baked into the platform firmware.
Like checking an ID card against a trusted database.
Exactly. This verifies the claimed identity. But then you need to prove the device actually possesses the private key corresponding to that certificate.
The real proof.
That's the challenge response authentication. The host generates a random number, a nonce, and sends it to the device.
Nonce, meaning number used once.
Yep. Prevents replay attacks, someone just recording and replaying an old authentication. The device has to sign this fresh nonce using its unique private key.
The key nobody else should have.
Right. The device sends the signature back. The host then uses the device's public key, which it got from the certificate it already validated, to verify that signature.
Ah, okay. If the signature matches, the device proved it has the private key, so it must be authentic.
You got it. That's the core identity proof. And once that's done, there's one more step: integrity measurement or attestation. Now that the host trusts the device's identity, it asks for cryptographic hashes, basically, summaries or digests of the device's critical firmware code and configuration data.
Like checksums, but cryptographically strong.
Exactly. The device provides these measurements, usually signed. The host compares these measurements against a golden manifest, a list of known good measurements for that specific device model and firmware version.
If they don't match.
Red flag. It means the firmware might have been tampered with. The host can then decide, nope, I'm not loading the driver for this device, or at least raise a security alert.
Wow, okay. So it's a multi-layered process. Verify the ID card, make the device prove it owns the corresponding secret key, and then check if its software looks exactly like it's supposed to.
That's a great summary. CMA gives you that foundational trust. You're talking to a genuine, untampered device.
And crucially, I assume this whole secure SPDM exchange is also how they set up the keys for the next step, actually encrypting the data.
Absolutely. You establish this trusted, authenticated channel first with CMS PDM, and then over that secure channel, you can safely exchange the keys needed for data encryption. You never send secrets over an untrusted link.
Perfect. Okay, so trust established. Now, protecting the data itself as it zips across the wire, that brings us to integrity and data encryption, IDE.
Precisely. With CMA having done its job, IDE steps in to protect the actual user data, the TLPs, while they're in transit. IDE is implemented as a new logical layer within the PCI stack. Its job is to provide 3 core security services against physical attacks, which confidentiality, keeping the data secret, preventing eavesdropping, integrity, making sure the data isn't modified, deleted, or messed with, and anti-replay protection, stopping attackers from capturing valid data packets and re-injecting them later.
And how does it achieve this? What's the underlying tech?
It uses a very strong, widely adopted standard, AES-GCM. That's Advanced Encryption Standard in Gelo counter mode. AES provides the confidentiality, the encryption. The GCM part is an authenticated encryption mode. It very efficiently provides both confidentiality and data integrity checking in one go. It's computationally efficient for hardware implementation too.
Okay, AES GCM. Now, are there different ways IDE can be deployed? Like, does it protect everything or just specific connections?
Good question. There are 2 main operational modes giving flexibility. First is Link IDE. Think of this as point-to-point security. It encrypts all traffic traveling over a single physical link, say between a CPU and a switch, or between 2 switches, or a switch and an endpoint.
So it protects that specific wire or trace.
Exactly. But if the data goes through a switch, the switch decrypts it, processes it based on the header, and then re-encrypts it for the next hop.
Okay, good for protecting individual links, but the switch sees the plain text data.
Correct. That's where the second mode comes in, Selective IDE. Selective IDE provides end-to-end security between a specific originator, like a CPU root complex, and a specific final destination, like an NVMe drive or a GPU.
Ah, so it goes through the switches without being decrypted.
That's the key difference. The data gets encrypted by the source device. It travels through any intermediate PCIe switches still encrypted. The switches can read the necessary unencrypted header parts to route the packet, but they never see the actual payload data in plain text. Only the final intended recipient can decrypt it.
Wow, that's powerful. That protects the data even if a switch itself is compromised.
Exactly. Selective IDE offers a much stronger security guarantee for the data payload itself, all the way from source to destination.
Okay, and how does this encryption actually work at the packet level, especially now with these fixed FLTs we talked about?
Yeah, the FLT structure makes IDE implementation much cleaner. So a few key mechanics. First, because the TLP itself is going to be encrypted, including its header, they needed a way to carry some essential info in the clear. So they add a small IDE TLP prefix before the encrypted TLP within the FLAT.
What's in that prefix?
Crucial stuff, like a stream ID, which tells the receiver which security context, which set of keys and parameters applies to this packet, and importantly, a single K-bit.
K-bit?
Yeah, it indicates whether the packet was encrypted with key 0 or key 1. PCIe supports having two active key sets simultaneously. This allows for seamless key rotation. You can switch from using key 0 to key 1 without dropping packets, crucial for long-running systems.
That's clever. What else?
Then there's partial header encryption, or PHE. You don't want everything in the TLP header encrypted because switches need things like routing information, but you also don't want to leave sensitive stuff like memory addresses completely exposed, as that could leak information.
Right, side channel attacks.
Exactly. So PHE allows specific sensitive fields within the TLP header to be encrypted while leaving the essential routing fields in the clear. It's a balance.
Okay.
And finally, remember, AES-GCM provides integrity checking using a message authentication code, or MHA.
Yeah, the integrity tag.
That MC adds overhead. To minimize this bandwidth cost, IDE supports MHA aggregation. Instead of adding a separate M tag to every single TLP, it can calculate a single MSE that covers a group of up to 8 TLPs traveling in the same stream.
Ah, so you stamp a batch of packets instead of each one individually. Saves bandwidth.
Precisely. Better throughput, less overhead. It shows they were really thinking about performance alongside security.
Okay, this is all incredibly well thought out. Encrypting the data, protecting integrity, doing it efficiently. But how do the two ends of that IDE connection, whether it's link or selective, get the shared AES-GCM keys to begin with?
Right, the crucial key management piece. That's handled by IDE key management, or IDE-KM. And here's where it ties back beautifully to CMA. All IDE streams start in an insecure state, no protection. To make a stream secure, the devices involved must first successfully complete that CMS PDM authentication process we discussed earlier.
Establish trust first.
Always. Once that authenticated SPDM channel is up, the IDE-KM protocol, which itself is defined to run over SPDM, securely exchanges or derives the necessary symmetric AES-GCM keys, initialization vectors, and other parameters for that specific IDE stream.
So CMA authenticates, then IDE-KM uses that trusted channel to set up the encryption keys.
Exactly. Once the keys are configured on both ends, the IDE stream is enabled, moved to the secure state, and POW all traffic on that stream is now protected by AES-GCM. And that K-bit mechanism allows them to update these keys periodically using the same IDE-KM protocol, again without interrupting data flow, essential for long-term security hygiene.
It really is a complete picture then. The speed push forces flip tees. Flip tees enable practical security. CMA establishes trust using SPDM. Then IDE uses that trust to set up keys and encrypt the data using AES-GCM over those flip tees. It all locks together.
It's a very coherent and robust security architecture. It ensures keys aren't flying around unprotected and data only flowed once devices are properly vetted.
Now, stepping back a bit, what's the bigger strategic impact of having this level of security built right into the I/O fabric?
Well, what's truly remarkable, I think, is how CMA and IDE together become a fundamental enabling technology for something much broader. Confidential computing.
Ah, okay. Protecting data while it's actually being processed.
Exactly. Confidential computing uses hardware features to create secure enclaves, trusted execution environments, or Ts. You hear about things like Intel PDX, AMD SEV. These Ts create protected virtual machines where you can run sensitive code and handle sensitive data, shielded even from the cloud provider's hypervisor or system admins.
But I see the potential problem. What happens when that super secure VM needs to talk to the outside world? Like read from a disk, or send data over the network. If it goes over standard, unencrypted PCIe.
You've just blown your security boundary wide open. All that sensitive data hits the PCIe bus in plain text, completely undermining the T's protection. It's a massive gap.
So how does PCIe 6.0 security help close that gap?
This is where another piece of the puzzle comes in. The T-Device Interface Security Protocol, or TDISP. TDISP is another protocol layered on top of PCIe, specifically designed to let these Ts establish secure communication sessions with I/O devices, like network cards or storage controllers, that are also TDISP aware. And here's the crucial link. TDISP doesn't try to reinvent secure transport. It relies on the underlying PCIe 6.0 security features.
Ah, so TDISP uses CMA to authenticate the device.
Exactly. The T uses TDISP, which in turn uses CMA to make sure it's talking to a legitimate, trusted I/O device.
And then TDISP uses IDE to encrypt the actual data flowing between the T and that device.
Precisely. TDISP leverages selective IDE to create that secure end-to-end encrypted channel between the confidential VM inside the T and the I/O device. This effectively extends the T's trust boundary to encompass its I/O operations. It makes secure I/O-intensive confidential computing actually practical. Without CMA and IDE as the foundation, TDISP wouldn't have a standardized, hardware-enforced way to work.
That's a really big deal, connecting the CPU's secure world to the outside world securely.
It is. It makes confidential computing far more useful for real-world applications.
And it's not just T's, right? There's another huge interconnect standard emerging that builds on PCIe 6.0 Compute Express Link, CXL.
Absolutely. CXL is built directly on the PCIe 6.0 physical and electrical layers. It uses the same PAM4 signaling, the same FLIT structure for its I/O traffic.
So does CXL adopt the same security model too?
Largely, yes. It shows a really nice convergence. CXL devices use the exact same CMS PDM protocols for authentication and attestation. So discovering and verifying CXL devices uses the same mechanism. For CXL.io traffic, which is basically standard PCIe traffic used for configuration and things like that, it just uses standard PCIe ID.
Okay, that makes sense.
And for CXL.cache and CXL.mem traffic, the protocols used for coherent memory sharing between CPUs and accelerators or memory expanders, they have their own specific IDE implementations because their FLIT formats are slightly different, but they're based on the exact same core principles as PCIe IDE, hardware-based link-level security using AES-GCM, operating on FLITs, key management tied to authentication.
So it's a unified approach.
Yeah.
Whether it's PCIe or CXL, the underlying security philosophy and mechanisms are aligned.
Very much so. It points towards a coordinated industry-wide strategy, secure the fundamental I/O and memory interconnects using these common building blocks like CMA and IDE principles. That's vital for the future of disaggregated computing and complex data centers.
Now, this all sounds fantastic, but implementing this isn't trivial, I assume. What are the practical hurdles?
Oh, definitely. For chip designers, the SO folks, they need to integrate new security IP blocks for CMA, for IDE, for the crypto engines. That adds silicon area, power consumption, design complexity.
And testing it all must be a nightmare.
Verification is a huge challenge. Validating these complex security protocols, ensuring the crypto is implemented correctly, checking all the state transitions for key management. It requires specialized expertise, tools, and a lot of simulation and testing cycles.
What about performance? We talk about lightweight FEC and MASI aggregation, but does adding encryption add latency or reduce bandwidth noticeably?
There is some overhead. Hardware decryption adds a small amount of latency, maybe a few nanoseconds per hop for Link IDE. The IDE prefixes and MAC tags consume a little bit of bandwidth, and the initial authentication and key exchange take some time during boot up. But the architectural choices clearly aim to minimize this. The very low latency FEC, the AMMARI aggregation, the hardware acceleration of AES-GCM, it's all designed to make the performance impact acceptable for even demanding applications.
Like HPC and AI you mentioned earlier.
Exactly. Those markets need maximum bandwidth and strong security, especially with huge valuable AI models and datasets. So they are aggressively adopting PCIe 6.0 and its security features.
Right.
Data centers, cloud providers, they see the value immediately.
What about us regular folks? When do we see this on our desktops or laptops?
The consumer PC market. That's going to be much slower.
Why is that? Cost? Complexity?
Both. PM4 signaling itself is more complex and costly to implement on motherboards and in components. Adding the security silicon adds further cost. Honestly, for most consumer use cases today, the bandwidth of PCIe 4.0 or 5.0 is plenty, and the sophisticated physical attack vectors that CMA and IDE protect against are less of a primary concern than in a multi-tenant data center.
So PCIe 5.0 might be the high end for consumers for a while?
I think so. We probably won't see widespread PCIe 6.0 in consumer PCs until maybe closer to 2030, just a guess, but it'll take time for the cost to come down and the need to really justify it there. PCIe 5.0 will likely reign for a good while yet in that space.
Okay, so summing this all up then. PCIe 6.0 really feels like a turning point, not just another speed bump, but a fundamental redesign where security, driven by those initial physical layer challenges, got baked in from the start. This combination of CMA for trust and IDE for protecting the data seems like a really comprehensive hardware-level defense.
It really is.
Yeah.
And importantly, these aren't just isolated features on the PCI link itself. They're foundational. They are the critical enablers for system-level security goals. They make protocols like TD-ISP possible, which closes that crucial I/O security gap for confidential computing. And the alignment with CXL security shows this isn't just a PCIe thing. It's setting a new baseline for secure, high-speed interconnects across the industry. It creates a much stronger, unified posture against physical attacks and tampering for the next generation of computing.
So as we wrap up, here's something to think about. Consider how much you rely on the cloud, right? Whether you're explicitly using it or it's behind the scenes in AI tools, financial apps, even online games. What new possibilities open up when the very hardware pipes carrying your most sensitive data have this level of built-in, hardware-enforced verification and encryption? Not just in those giant data centers today, but maybe eventually on your own devices as these technologies mature and trickle down. What could that enable? Definitely some food for thought. Thank you for joining us for this deep dive.